Hello and welcome to my video. Today I am going to visit one of my old videos, namely this particular video. You can check the link to this video at the description or at the top right corner. In that video, I have calculated the minimum distance of length PQ, but that minimum value is not the true minimum distance between two lines AC and FD, because in that problem, points P and Q move with specific speed and their positions are specifically given as a function of time, so it is only a minimum distance under that specific condition, not the actual minimum distance between two lines. So here, let us assume that both point P and point Q move freely along lines AC and FD respectively. Then, what is the minimum value of line segment PQ? In other words, what is the distance between skew lines AC and FD? Two lines in a space that are neither parallel nor meeting each other. In my old video, I have solved the problem using coordinates, which was the simplest method. So here I will present you the coordinate method first. In my old video, positions of P and Q can be expressed using a single variable, the time t. But here, P and Q now move freely, so we need two variables. First, the position of P. Let us take coordinates like this, with point A being the origin. Note that vector AC is 1, 1, 0. You can think of this as the direction vector of the line AC. Therefore, position of P can be expressed as some real number s times that direction vector, which is s, s, 0. And we do the similar thing for point Q. Here, vector FD is given as -1, 1, -1. Here we take f as an arbitrary starting point, then the position of q is expressed as this starting point plus some real number t times direction vector fd, which is 1, 0, 1 plus t times -1, 1, -1, therefore 1 minus t, t, 1 minus t. So these are the positions of P and Q using two variables, s and t. Now distance PQ square is expressed as two variable function using s and t, which is 1 minus t minus s square. And for the y coordinates, we have t minus s square. And for z coordinates, we have 1 minus t square. Now let's expand. When expanding this part, we have to use this formula, now with a couple of minus signs. So for that part, we have 1 plus t square plus s square minus 2t plus 2st minus 2s. And for this part, we have t square minus 2st plus s square. And for this part, we have 1 minus 2t plus t square. Now notice that 2st terms cancel out, and we have 2s square plus 3t square minus 2s minus 4t plus 2. This is a quadratic function of s and t, and we can transform into vertex form for both parameters. So we write 2 times s square minus s plus 3 times t square minus 4 over 3t plus 2. So in order to complete the square, we add 1 over 4 here and subtract 1 over 4. And here we have to add 2 over 3 square, which is 4 over 9. And of course we have to subtract it. So these parts become complete square. So we have 2 times s minus 1 over 2 square plus 3 times t minus 2 over 3 square. And we have to calculate the rest, which gives 1 over 6. Now since s and t can have any real values, pq square is minimum when s equals 1 over 2 and t equals 2 over 3. This means that distance pq is minimum when coordinates of p and q are like these, and the minimum value is square root of 6 over 6. And this is the true distance between skew lines AC and FD in the 3D space. Now let us introduce the second method. Here, lines AC and FD given in this problem are very special. They are the face diagonal and the main diagonal of the cube respectively, so we can solve this problem in classical way. That is, without using coordinates. Now let us recall the distance between a point and the straight line. the distance is minimum when this angle is right angle. That is, these two lines are perpendicular. Similarly, the distance PQ is minimum when line PQ is perpendicular to both lines AC and FD. This gives the position of P as the midpoint of the line segment AC, because then both points P and Q are on the plane BDF, the plane that is perpendicular to line AC. But point Q, which is the foot of perpendicular from point P onto line FD, is not a midpoint of the line segment FD. So we have to let QD equals X, which means FQ equals square root of 3 minus X. And this length is of course 1, and moreover, distance BP and PD are both square root of 2 over 2, and by the Pythagorean theorem, we can calculate the length of PF, which is square root of 1 square plus square root of 2 over 2 square, and therefore square root of 6 over 2. So this length is square root of 6 over 2. Now this setting allows us to find the value of X like this. PQ square equals PD square minus QD square by Pythagorean theorem, and PQ square is also equal to PF square minus FQ square, also by the Pythagorean theorem. Therefore, we can set up equation using this relation. Here PD square is square root of 2 over 2 square, and QD square is simply X square, and PF square is square root of 6 over 2 square, and FQ square is square root of 3 minus X square. So if we expand, we obtain 1 over 2 minus X square on the left hand side, and 3 over 2 minus 3 plus 2 times square root of 3x minus X square. So we can cancel out these X square, so we have X only here. So if we solve this, we obtain X equals square root of 3 over 3. Therefore, we can calculate the length PQ using this part, which is square root of PD square is square root of 2 over 2 square, and QD square is square root of 3 over 3 square. So we obtain square root of 1 over 6, which is square root of 6 over 6. The same result as in the first method. So that was all for this video. I have revisited this problem just because I wanted to clarify that this is the actual distance, the shortest path between these two lines. Thank you for watching, and I will see you in another video.